Right, so let's take a look at an example of when we would want to use one of our really strong bases, such as LDA. And this would be for alkylation as one example. So we have our carbonyl with our alpha carbon and alpha hydrogens. Here we're going to insert a strong base, LDA. So we're going to completely deprotonate everything and completely transform it to the enolate. In terms of drawing out LDA, you probably should know what LDA is, but it's kind of a pain to draw. So I'm totally fine with you just drawing LDA and then a lone pair. And let's add a negative charge to it, just to make it a little bit more realistic. Attacks this hydrogen to form the enolate. And then this will be a one-way arrow because our base is extremely strong. All right, now that we have our enolate form, what we can do is we can add some kind of alkyl halide to it. And we have to make sure that when we add the alkyl halide, there's not any base remaining, because then it'll just do an E2 elimination, right? So we just have to have just the enol, or just the enolate, and all our base used up. And so then it'll just do an SN2 reaction. So this will kick down. We'll attack with the nucleophilic carbon and then do an SN2 reaction. And now we've just created a carbon-carbon bond, and we've alkylated our alpha carbon position. Note this is an SN2 reaction, so all the usual components for the SN2 reaction count. Remember, your R can be methyl or primary, right? No secondary, no tertiary. Allylic is fine. Right, allylic means the halogen is next to the pi bond, not on the pi bond. Or benzylic, right, next to the phenyl ring, but not on the phenyl ring. Those are fine. And then, of course, in terms of whatever your X is, right, you can use like a tosylate. So if you want to get rid of an oxygen, or a halogen, right, iodine, bromine, or chlorine. Fluorine, not a strong acid, not a good leaving group. Let's take a look at some more nuances in this reaction. So what if we have an asymmetrical carbonyl, right? On this carbonyl, we have two alpha positions. One is more substituted than the other. Can we control where we get the alkylation? And the answer is yes. If we go to the right here, we'll use our LDA. And then we'll do this at very cold temperatures, so -8 degrees Celsius. And then after that, we'll add our RX. And then we'll get substitution at the less substituted position, right? So your R will add there. And then if we think about it, what we're doing here is we've got a bulky base. And so what we're forming here is the kinetic product, right? And that's coming from this intermediate. Right, that bulky base is going to form that less substituted alkene. If you're wondering why -78 degrees Celsius, that sounds like such a random number. That's dry ice temperature. So it's just a good cold temperature that's relatively easy to use in the lab. All right, what if we wanted it in the more substituted position? Then we would use something like sodium hydride, a non-bulky base, but that's still going to cause an irreversible reaction because the hydride combines with an H+ and then leaves as H2 gas. Or do this at warmer temperatures, usually room temperature, and then add your alkyl halide. And this is going to go through the more substituted enolate intermediate. Right, and then this is our thermodynamic product. Right, non-bulky base, higher temperatures, the more substitute alkene, which will then attack. Overall, pretty good reaction. There are a lot of issues in terms of like real life applications with this reaction, but on paper it looks great, and we're going to stick with on paper for the most part.